Welcome on Livestream 2 for the CIRPe Global Web Conference 2019. For those of you who have just started watching us, we have
functional and geometrical requirements. As the number of supplies increases, the number of available solutions for customers increases too, resulting in a more complex decision-making process for the customers. In such big and complex information environment, a solution recommendation system can play a crucial role in decision-making process by taking into account customer past experience as a value choice. In this context, this paper proposed Hello.
Welcome back. We had a technical problem, so we are back online on Livestream 2, and we are going to directly continue with our program with the first presentation of Alessandro Simone from China, Alessandro Caggiano from Italy, Bing Deng and Liu Wenbun from Israel. The paper is entitled A Deep Learning-Based Decisions Portal for Solution Recommendation in Cloud Manufacturing Platforms. Please feel free. I excuse our technical problems, and we are going to right away continue with the first presentation of our colleagues from Alessandro Simeone. Welcome back on Livestream 2. I excuse our technical problems. We will directly continue with the first presentation of our colleagues, Alessandro Simeone from China, Alessandro Caggiano from Italy, Bing Deng and Liu Wenbun from Israel. The paper is entitled A Deep Learning-Based Decisions Portal for Solution Recommendation in Cloud Manufacturing Platforms. We are looking for your presentation.
Hello everyone, and welcome to my presentation entitled A Deep Learning-Based Decision Support Tool for Solution Recommendation in Cloud Manufacturing Platforms. I'm Bing Deng from Central University, China. I'm going to give a brief overview of cloud manufacturing related issues and describe the paper objective. Then I'm going to illustrate the framework and the methodology adopted for this work, which will be exemplified through a simulated case study. Then I'm going to report and discuss the results and draw some conclusions. With reference to seat marketing industry, the fluctuations of the demand volume and Hello everyone, and welcome to my presentation entitled A Deep Learning-Based Decision Support Tool for Solution Recommendation in Cloud Manufacturing Platforms. I'm Bing Deng from Central University, China. I'm going to give a brief overview of cloud manufacturing related issues and describe the paper objective. Then I'm going to illustrate the framework and the methodology adopted for this work, which will be exemplified through a simulated case study. Then I'm going to report and discuss the results and draw some conclusions. With reference to seat marketing industry, the fluctuations of the demand volume and product variety can have a negative impact on the resource efficiency. To tackle this issue, the idea is to reduce the amount of material waste, especially at industrial network level. This can be achieved by combining multiple seat marketing orders on the same metal sheet by performing a lasting operation aimed at reducing the total waste material. An interesting tool in modern industrial context is cloud manufacturing, which can allow for the dynamic sharing of distributed resources in order to improve the resource efficiency in smart industrial networks. Within the considered industrial sector, the interconnection of various types of users, such as suppliers and customers, can be carried out by generating a number of solutions at cloud level based on functional and geometrical requirements. As the number of supplies increases, the number of available solutions for customers increases too, resulting in a more complex decision-making process for the customers. In such big and complex information environment, a solution recommendation system can play a crucial role in decision-making process by taking into account customer past experience as their new choice. In this context, this paper proposed the conceptualization and the development of an intelligent recommendation decision support tool. This paper considers a modular-structured cloud manufacturing platform developed by the authors in previous works, which is summarized in this slide. First, users access to the platform via a database module aimed at gathering customers and supply instances, including information and details on their orders, such as quantity, material, geometrical features, deadlines, locations, and clearly the code file. Such information are then processed by an intelligent assessment and optimization modules, which first verifies the function compatibilities based on materials, thicknesses, technologies, and tolerance. Subsequently, this module performs a user match, considering the compatible instance, and generates a number of manufacturing solutions, according which are optimized for each pair of users. The cloud platform is endowed with a twofold decision-making module for suppliers and customers, respectively. From a supply perspective, the solutions are characterized by their surface utilization rate and deadline evaluations, where the customers assess solutions according to a number of parameters ranging from surface utilization rate, energy consumption, persist time, distance cost, number of supplies, and supply rating. This paper proposed a solution recommendation system that performed an intelligent solution ranking procedure. This is enabled by the use of deep learning paradigm that allows to capture patterns among the customer's supplies, solutions, and customer choice history. The solution recommendation system is firstly trained to use users' features as input data, namely quantity, available time to completion, area and perimeter of customer instance, and quantity, current speed, machine power, area and perimeter of supply instance, along with the supply rating. Other inputs are solution features, consisting in surface utilization rate, processing time, energy consumption, and distance for a given solution. Additional features focus on material properties, such as material cost, thickness, and so on. The ranking system is configured here as a multi-class pattern recognition problem. Hence, the system is trained adapting as target a number of solution tiles, representing the likelihood of a certain solution to be selected. In this way, it is possible to train the neural network with the aim of recognizing patterns amongst the customer and supplier instance solutions and user selections. Once the system is trained, it can be fed with a new list of feasible solutions for a given customer, and it will output a ranked list of solutions sorted according to their tier in descending order. The customer is then allowed to select the best solution according to its own requirements. In case the customer selects a solution which doesn't belong to Tier 1, the system will update the tier according to the customer selection in order to incorporate the information on the new customer selection. Tiers are updated based on a hierarchical clustering approach. In particular, each solution feature is initialized in its own cluster. Then the pairwise Euclidean distance between all the solution pairs is computed and linked to be represented as the dendrogram on the right of this slide. The selected solution belongs is then updated as the new tile 1, and consequently, the further clusters are assigned tile rank in descending order. To better exemplify the proposed method, a simulated case study is reported with reference to seed mud cutting. In this work, we consider a total of 30 different customers. Each customer can choose among 83 compatible solutions. For simplicity, all the solutions reported in the dataset have been demonstrated to be perfectly compatible for both users, and the material features have not been taken into account. This table shows for each solution the import features made of customer, supply, and the solution features, along with the target class represented by the tile. It was possible to assign a tile to each solution according to some likely ground truth criteria illustrated in this slide. In particular, we try to simulate the customer point of view in various decision-making scenarios. For example, if a customer is in a hurry, which means less than 96 hours from the order placement to the deadline, such customer will likely choose a solution characterized by the minimum process time. On the other hand, if a customer can rely on a supply which is geographically close or with low transportation costs, it will likely choose a solution with least distance cost. For customers demanding special geometrical requirements, the supply rating is surely the main driver for solution selection. Considering the batch size, customers with large batch size will choose a solution with very high surface utilization rate, and the customers with low bit size will choose a solution with minimum energy consumption. Having built the input and training dataset, at this point it is possible to build the neural network architecture. In this paper outlined with 4 hidden layers, and each hidden layer has 28 rows. For hidden layer, we use hyperbolic tangent as the activation function, and for output, we use softmax. In order to train the system, we use gradient descent with a learning rate equal to 0.02. It is time to illustrate and discuss the results obtained with our proposed method. Firstly, the system was trained using data related to only 20 customers, and the system achieved a training accuracy of almost 80% in tile classification. The trained system was then used to test the recommendation system on 3 new customers, and the system showed that 2 customers would actually choose a solution classified as tile 1, resulting in a correct classification, where 1 customer would choose a solution in tile 3. The customer choice was again simulated using a ground truth criteria described below. In this case, a tile update procedure needs to be performed for customer 21 to update the cluster to which the selected solution belongs as tile 1. Going on, the information on the 3 test customers of the previous one were appended to the training set. In this way, the system was retrained using 23 customers' data, obtaining a training performance of nearly 80%. 3 new lists of solutions were fed to the retrained system, and the results show that 2 of these new customers would choose a solution classified as tile 1, where 1 customer would choose a solution classified as tile 2. Again, there is need to update the tiles using the hierarchical clustering-based procedure illustrated before. Finally, the 3 customers' data from run number 2 were added to the training set. In this way, the system was now trained using 28 customer data, obtaining a training performance of 86%. This time, the trained system was used to test for new customers, and the results show that, according to the ground truth criteria, all of them would choose a solution classified as Tier 1. In this case, there is no need to update the tiles. Now it's time to make some conclusions. In this paper, we propose an intelligent decision-making support tool based on deep learning and continuous updating to be implemented in a cloud manufacturing platform. Despite a long exceedingly outstanding performance in terms of learning accuracy, the system proved to be an effective decision-making support tool, able to recognize patterns within user requirements and generate solutions. Our future works will focus on improving the system capabilities by adopting a large dataset, along with the development of alternative learning techniques, such as reinforcement learning. Thank you.
Thank you for your presentation and sending the video. We have a delay around 10 minutes, so I would like to continue with the second paper for this session just after that and skip the question and answer session. Please feel free to comment us or the authors for any further information you are interested in. The second presentation of this session is entitled AI-based combined scheduling and motion planning in flexible robotic assembly lines, and this contribution is from our colleagues from the Laboratory for Manufacturing Systems and Automation from University of Patras, Greece. The authors are Niki Kausi, Demosthenes Demosthenopoulos, Alessandros Sterios, Mattiakis, George Michalis, and Sotiris Makris. We are looking for your presentation, Demosthenes.
Hello, my name is Demosthenopoulos Demosthenis. I work as a research engineer in Laboratory for Manufacturing Systems and Automation, LMS. I would like to present you the paper entitled AI-based combined scheduling and motion planning in flexible robotic assembly lines. Under this presentation, the problem of mobile robots integration into dynamic production systems will be described. Additionally, the objectives of the proposed approach and the detailed implementation will be presented. The proposed system has been implemented in a case study inspired from the automotive industry, and based on the outcome, the conclusions in the outlook of this work will be listed. The traditional production is mostly based on fixed automation and manual production. The fixed automation is very efficient for massive productions, but it lacks flexibility, as the resources in the processes are fixed and pre-programmed. As a result, the introduction of new product variants is highly money and time consuming. On the other hand, manual production is highly flexible, but it creates ergonomic issues for the workers as they are forced to handle heavy loads. The latest trend to overcome these challenges is EU Foster the Human-Robot Collaboration, since it aspires to keep a low production cost and to increase factories' reconfigurability by combining the skills of both humans and robots. A reconfigurable factory could be enabled by a smart robot control system. Inspired by that, an efficient decision-making framework is developed that targets on the dynamic work balancing among the human operators and robot resources and on the safe and efficient collaboration between them. The proposed system is able to monitor in real time the production status and make decisions about the task allocation based on the current resources availability and capabilities. In order to develop an effective control system, a multi-level decision-making approach is considered as the best strategy. As already mentioned, the ultimate goal is to distribute dynamically and efficiently the workload among the resources, taking into consideration real-time changes in working environment. To this end, the decisions made by the implemented framework are based on the two-way interaction between line-level and resource-level decision-making. This interaction is taking place via a dynamically updated digital twin. The digital twin exchanges data in real time with sensors, MRP motion planners, search-based algorithms, and multi-criteria decision-making algorithms in order to generate the optimal scheduling. The hybrid production systems are in most cases characterized by high complexity. In order to efficiently manipulate systems with that level of complexity, intelligent planning algorithms are required. To this end, the process and the working environment are modeled with respect to a hierarchical modeling using artificial intelligence techniques. As we can see in the figure, a 5-level hierarchical structure has been used to model the process. The scheduling and the task allocation take place in layer 4, while the motion planning in layer 5. Also, for the facilities representation, a 3-level breakdown of shop floor, assembly line, and assembly station has been implemented. The decision-making framework developed to manipulate hybrid production systems is based on some clearly defined principles and follows some strictly determined steps in order to achieve the most efficient task allocation among the resources. These steps are the following: resource suitability evaluation, generation of the alternative scenarios, evaluation criteria ranking, evaluation of the generated alternatives based on the selected decision-making criteria, selection of the highest scoring alternative as the optimal scheduling solution, and motion planning. Each of these modules will be presented in the upcoming slides. The resource suitability module is designed to prevent the task planner from time-consumingly evaluating unrealistic alternatives. The resource suitability evaluation function is based on the relation between each operation's needs and each resource's capabilities. For example, as presented in the figure, a screwing operation needs a specific screwdriver to be completed. So, the resource to assign to execute this operation must have this tool available. Another major factor in resource suitability evaluation is the parts handled in each operation and their individual characteristics, like their weight, for example, which must be lower than the suitable resource's payload. The next step in the decision-making process is the generation of the alternative tree. As it can be seen in the figure, each branch of the tree represents a complete alternative schedule. Each alternative is formed as a combination of a specific operation and the resource this operation is assigned to. The black boxes in the figure represent alternatives that were randomly selected by the decision algorithm not to be checked. Therefore, the scheduling process was terminated at this point. After forming the alternatives, the preferable evaluation criteria are selected and used to evaluate the generated scenarios through the digital twin. These criteria and their weight factors are pre-selected by the user based on the production system's needs and objectives. Under this implementation, the chosen decision-making criteria are minimizing part flow time, minimizing payload handled by the human operators, minimizing distance covered by the mobile robots, and maximizing resource utilization. All these criteria have been mathematically defined via equations. The value of each criterion is normalized and the utility value is calculated. The alternatives that are considered as feasible after the resource suitability control are evaluated and rated based on the utility value using the presented equation, and through this process emerges the highest scoring alternative as the optimal scheduling solution. As already mentioned, each alternative is simulated and evaluated via the digital twin. So, in order to simulate the execution of each alternative and take the information needed for the evaluation process, like time estimations from the digital twin, the correspondent operations need to be translated into robot actions. This connection is proposed to be accomplished through a templated method. After experimenting, each individual type of operation has been linked to a group of robot actions, creating a unique template for each type of operation. These templates are filled with information about the real world through the digital twin as well, and are used to simulate the robot's behavior during each alternative. The whole framework architecture is based on the interaction between three individual subsystems. These systems are the following: the digital twin database. In this module are saved all the information and data about the process and the real world. The planning tool and criteria evaluation functions. These functions are responsible for generating the alternative tree and evaluating each alternative based on the selected criteria. The robot program generation. This module's role is to convert the operation-based schedule extracted by the task planner into a robot action-based executable program. All these modules are integrated in a central platform allowing their online communication and exchange of data and information in real time. The proposed methodology has been applied to a collaborative scenario inspired by an actual production line of the automotive industry. In particular, the proposed framework has been implemented with the use of data from the front axle assembly line of a passenger vehicle. As presented in the figure, the current state of this assembly line involves 4 assembly stations where all the tasks included in the front axle assembly are taking place. Station 1 right damper assembly, Station 2 left damper assembly, Station 3 screwing operations, and Station 4 cabling station. In this case, the current production line employs 3 human operators in total. The main issues with this approach are ergonomic, as the human operators are forced to repeatedly carry and manipulate the 6 kg dampers. Also, this assembly line lacks flexibility, as the screwing machine is able to assemble only one car model, while the other 2 models that produced from this line are assembled manually. In the proposed production line, 2 MRPs will be introduced to take over some of the handling, inserting, and screwing operations. Thus, Station 4 will not be necessary anymore, as the operations taking place under this production phase will be transferred to Stations 1 and 2. Moreover, one of the MRP manipulators will undertake all the screwing operations, leading to the elimination of Station 3 as well. Also, under this approach, all 3 car models are produced from the assembly line. Finally, after the introduction of the robotic manipulators, only one human operator will be needed to work in the remaining stations, allowing the exploitation of the other 2 workers in different posts where the human capabilities are needed. Based on this case study, experiments and simulations were conducted in order to investigate the performance of the proposed system. Both systems were evaluated based on the same criteria metrics, and the arising results were used to compare their performances under the same conditions. Gantt charts and resource utilization diagrams are also presented for both manual and hybrid assembly model in order to compare the resources utilization. In this slide are presented the results for the manual assembly model. It is shown that under this approach, each human operator is only taking part in a small fraction of the overall production process. On the other hand, as presented in this resources utilization diagram, under the hybrid production model, the human operator contributes to a much greater degree in the overall production. By comparing the 2 models, it is evident that the hybrid production system presents higher performance validation metrics in every evaluation criterion used. The proposed approach achieved a significant reduction in flow time while reducing the payload handled by the human operators. As for the resources utilization, it is obvious based on the diagrams that under the hybrid production model is achieved a much more balanced task allocation among the resources, the idle time of each resource is significantly reduced, and the remaining human operators can be used in other more intellectually demanding tasks. Summarizing, this case study discussed the implementation of a decision-making framework which combines efficiently scheduling and motion planning based on AI in robotic assembly lines. So, with implementation of this architecture can be achieved many significant goals like optimal task allocation, easy rescheduling, optimal and realistic motion plans, and efficient exploitation of human capabilities. As for the future work that needs to be done, the identified next step for enhancing the proposed method is the implementation of the developed framework in larger scale application. Also, future studies should target on how the integration with the factory's legacy system will be accomplished. This work has been funded under EU AIDS 2020 project Mobile Dual-Arm Robotic Workers with Embedded Cognition for Hybrid and Dynamically Reconfigurable Manufacturing Systems, TOMAS. Thank you very much for your attention.
Thank you for sending us this presentation. Because of the delay we had at the beginning of the stream, we are going to skip the question and answer sessions for this presentations, and the last presentation and the next one are from the same lab from University of Patras. That's why we are going to connect to both authors after the third presentation, and we'll combine welcome them in the studio after the third presentation. Let me just give you a short overview about the third contribution from the Laboratory for Manufacturing Systems and Automation from University of Patras in Greece. The next presentation is entitled Model-Based Reconfiguration of Flexible Production Systems, and the authors of this paper are Christos Gronelukos, Niki Kausi, Angelos Christos Bavelos, Sotiris Ivaletois, Christos Giannouliou, George Michalos, and Sotiris Makris. We are looking forward to your presentation.
Hello, my name is Angelos Christos Bavelos, and I am working as a research engineer in the Laboratory for Manufacturing Systems and Automation of University of Patras in Greece. In this session, I will present you the paper entitled Model-Based Reconfiguration of Flexible Production Systems. The contents of this presentation are as follows. First, there will be an introduction regarding the subject of this paper and the challenge that it attempts to overcome. Then the initial approach to the problem will be explained and the implementation will be analyzed. The performance of the presented work will be shown in the case study, and I will conclude with the conclusions and future plans of this work. Currently, the traditional product systems are suffering from fixed logic and pre-programmed operations. These limitations affect the flexibility of the system to non-scheduled changes and enhance the uncertainty of the shop floor. Current execution control infrastructures are not mature enough to support the integration of modular robotic systems that require continuous real-time environment and process perception. Also, existing perception technologies and equipment cannot ensure a robust implementation under a complex industrial application. This work aims to overcome the existing limitations by implementing a modular execution control framework, utilizing a digital twin created through the use of several perception sensors, and enabling a robust but yet adaptable behavior for the mobile robot platforms, which are explained next. The framework is created to practice on a hybrid dynamic reconfigurable shop floor enabled through mobile dual-arm workers. These workers are called the mobile robot platforms, or else MRPs. The hybrid production paradigm foresees the use of mobile robot platforms. These workers must navigate autonomously inside the shop floor and undertake multiple assembly operations, such as handling and screwing. They should also act as assistants to human operators. To enable such autonomous flexible behavior, it is vital to efficiently organize all production entities and reason over the perceived environment using real-time data coming from the shop floor. The robotic systems should be able to receive information from multiple sources. They should also be able to identify objects, estimating the pose accurately, and be able to understand the 3D structure of their environment, so they can interact with it as well as with other resources for the completion of a task. The suggested execution control framework has two levels: the process level reconfiguration, which has 3 submodules, and the resource level adaptation, which has 2 submodules. For providing continuous input to the cognition modules of each level mechanism, a digital twin is required, which is updated real time through the MRP sensors. The output of this is a visual representation of the software status and functionalities such as simplified control integration and sensor data sharing, a unified semantic data model, and real-time robot behavior adoption. The workload coordinator shown in this image is responsible for decoding the production plan into robot actions and sending these actions for execution. The process reconfiguration level enables the adoption at runtime of the process based on the software status. Dedicated interfaces with perception modules will allow the online reconfiguration of the execution. It is comprised from 3 modules. Firstly, the object detection, which accurately detects the position of a part, such as a damper, in order for the robot to be able to manipulate it. It can be used with different detection algorithms for the detection of different objects. The global navigation is referring on the motion of the whole mobile platform inside a known map of the shop floor. The map contains static obstacles that are defined through a mapping process, which takes place prior to the execution of production. New and unknown obstacles that may appear can be included and avoided through the online information that the digital twin provides. However, the navigation is not entirely accurate when moving from station to station, and the error must be compensated. That is the job of the accurate localization, which imitates a virtual docking application as shown in the image. The resource reorganization is the lower level of execution control framework, and it is responsible for the adaptation of navigation paths and arm motion trajectories. The main goal of this level is to avoid potential collisions with other resources and unmapped obstacles inside the environment. In order to do this, two modules are included. First, the Arms and Torso Motion Planner, which exists to ensure safe and collision-free motion planning for the arms and torso of the MRP. It utilizes information from the digital twin concerning robot current state and kinematics, objects that are rigidly attached and obstacles to avoid. The Platform Path Planner is responsible for the online path planning of the platform, and its main responsibility is finding a minimum cost plan from start point to end point, considering the static and dynamic obstacles of the working environment. Concerning the implementation of the software for the framework, it is based on the robot operating system principles and takes advantage of its interfaces such as topics, services and actions. All its modules are developed with a C++ programming language. For the object detection module, several perception methods were tested, such as contours, which detect the object by detecting its outline, and the PPF and ICP algorithms, which are surface matching algorithms that find the spatial relation that aligns two 3D point sets. These methods are augmented by the use of fiducial markers. The global navigation module is responsible to retrieve sensor data and semantic information like the known map of the working area from the digital twin. All these data are fused together and a cost map is created with all the static and dynamic objects. The accurate localization module works by detecting fiducial markers such as apple tags or alvar tags. The detection creates a frame in reference to the camera frame. Then the platform planner uses this frame to commence the virtual docking. Platform Path Planner included in robot level adaptation includes two subcomponents, the Path Planner for navigation and the mobile-based controller which is responsible for the accurate localization of the MRP. The path planning component is implemented based on the ROS navigation stack for mobile robots. This provides great flexibility in integration of different mobile robots. Regarding the mobile-based controller, this controller is a closed-loop PID velocity controller of the mobile which takes as feedback the position error between the platform and the detected tag. The Arms and Torso Motion Planner is responsible to provide a valid motion of robotic arms and torso of the robot. This module is developed based on the MOVEit framework. Online update of the planning scene is established from the sensor data that are provided. An occupancy grid is used from the online planning component for ensuring collision-free trajectory planning. A parallel motion of the two arms and the torso is also provided from the kinematic planners of MOVEit. The communication with the robot arms and the torso takes place through the ROS hardware interface. Moving on to the case study, the suggested framework has been implemented in an assembly line of the front suspension of a vehicle from the automotive industry for the front axle assembly. In this scenario, the robot moves from station to station, performing handling and screwing operations, which were previously done by manual labor, thus increasing the automation of the process. In collaboration, a human operator performs cabling and assembling tasks in the stations. The cell of the assembly line includes three stations: the pre-assembly table, the compression machine, and the final assembly area. The mobile robot must pick the pre-assembly damper from the pre-assembly table, then it must navigate to the compression machine and place the damper there, where it will be compressed. The robot performs additional handling tasks of an alignment rod and a nut on the compression machine. Then it picks the compressed damper and it must navigate to the final assembly area, where it will place the compressed damper and perform screwing operations. The proposed framework enables both online processor configuration and MRP's actions adoption in case of any mechanism's failure and/or unexpected human actions inside the robot's working area. The sensors that are used for this implementation are the SICK Microscan, a Microsoft Kinect, an Intel RealSense, and two RoboCeption cameras the RC Wizard 65 and 160, and they are all placed as shown in the image. The assembly process starts with MRP's action for damper removal from a pre-assembly table. First, the damper needs to be detected with the use of the RC Wizard 160 stereo camera sensor, which is mounted on the right arm of the MRP. Based on the outcome of the detection, the motion of the robot arms for the grasping of the damper is calculated online. One marker is placed in a specific distance from the damper's fixture in order to perform accurate localization of the MRP in reference with the pre-assembly table and resolve big errors due to the navigation of the MRP. After grasping the damper from its fixture, the MRP starts to navigate towards another workstation, the compression machine area. The mobile-based navigation process is based on real 2D data, which comes from laser scan sensors placed on the MRP's platform. The navigation map is constantly up to date with the collision objects inside the robot's working area. Both operators working around the mobile robot and static machines can be detected as collision objects. After this framework's implementation, the mobile robot's navigation plan is dynamically updated in case of an unexpected motion of human operator close enough to the robot's body. Virtual docking actions are executed to minimize the deviation between navigation goals and robot's position after the navigation actions, based on the detection of Apple tag markers, which are placed on each workstation. Following the same procedure with the damper's detection process, the mobile robot detects the damper fixture using one Roboception RC Wizard stereo camera inside the compression machine's area and executes the damper placement action. The communication and the message exchange between the modules for the aforementioned tasks are shown in this image. Finally, as to the benefits of the proposed framework, it provides the interfaces for integrating mobile multi-arm robots with various cognition components. It minimizes the difficult teaching procedures and makes it possible that the layout of the workstation can be changed without hampering the robot's task execution. As to future work, the aim is to integrate the execution control framework with a physical robot setup in order to validate its performance and with high-level decision-making mechanisms, allowing task reallocation based on real-time production needs. At this point, I would like to acknowledge the European-funded Project Thomas, which partially supported this research. You may find more details on the project's website and public media. Thank you very much for your attention.
Thank you for your presentation. We have combined the questions and answer sessions for the last two presentations since the authors are from the same lab, from the Laboratory for Manufacturing Systems and Automation from the University of Patras in Greece. So I would like to welcome our contributors on our Skype call now. Hi, can you hear me?
Hello.
Yes, hello.
Yes, we can hear you.
Great. Thanks also for your flexibility. So we have one question for each of you, and the first question goes for the first paper about IE-based combined scheduling and motion planning in flexible robotic assembly lines. You have mentioned that you have some large-scale applications upcoming in the future. Do you have? Could you just comment on it? Are they in online, and which applications are you thinking about?
Yes, actually, at this point, we work on our case study, but as for future work, we plan to make some advancements in our framework in order to be applicable to larger scale applications. But at this point, we don't have anything yet.
Okay, thank you.
Thank you.
And the next question is for the paper entitled Model-Based Reconfiguration of Flexible Production Systems. Could you give us a bit more detail about the boundaries or limits for the task reallocation on shop floor?
Yes. One strong limit is that the malfunction of the robot, a mechanical malfunction, that it would not be possible to reallocate tasks for that. The human to intervene and fix that. There are some emergency cases that we have worked on, and the task reallocation works for that. But if a fuse burned or something like that, there would need to be an intervention, no reallocation there.
Okay.
Another would be a big error. We are trying to reduce that, but one example would be, it rarely happens, but when there is a big navigation error, then it may not be possible for sensors to perceive the necessary tag for the localization. But we are working on that.
Thank you very much. There's another question for your paper, which is already posted on YouTube live chat. Maybe you can also see it. Our commenter asks, can you give more information about the total distance covered for both approaches?
Let me check. Can you information covered for both approaches? The distance on the shop floor. That would be, well, the workstations have a distance between them of 2 or 3 meters. So it moves between 3 workstations. So that's about the right distance, if that's the question.
Maybe our commenter can recommend on your answer. I'm just
Yes,
waiting for a second to get the answer. I have not received any answers now. I would ask you as authors and also our commenter on YouTube to continue chatting on the same live chat and would like to continue with our program. Thanks a lot for being with us.
Bye. Goodbye.
Bye. Thank you. So as next, we have a contribution from our colleagues from the Institute for Factory Automation and Production Systems from the Friedrich-Alexander University in Erlangen, Germany. The paper is entitled Microservice-Based Architecture for Engineering Tools Enabling a Collaborative Multi-User Configuration of Robot-Based Automation Solutions. The authors are Eike Schäfer, Andreas Meyer, Jonathan Fuchs, Martin Ziabor, Janas Vondan, and Jörg Franke. We are looking forward to your presentation.
My name is Eike Schäfer of the Institute for Factory Automation and Production Systems der Friedrich-Alexander-Universität Erlangen-Nürnberg, and I'm very proud to present our paper Microservice-Based Architecture for Engineering Tools Enabling Collaborative Multi-User Configuration of Robot-Based Automation Solution in behalf of my colleagues. But why it is necessary to develop a microservice-based architecture? Aren't there existing technologies to address this problem? Due to technology complexity, there is actually no tool for small and medium-sized companies to support the planning of robot-based automation solution. So currently, they have to go to a system integrator. To build a multidisciplinary software solution, the microservice architecture is a perfectly fit. The idea behind a multidisciplinary software architecture based on microservices is very simple. There are different providers who have highly specialized knowledge about their topic: simulation, configuration, export, visualization, and these highly specialized providers develop a microservice. And these microservices can be used in different software packages. A platform operator is combining for a specialized use case, like in our case, robot-based automation solution and their configuration, and builds with these services a highly specialized and customer-specific solution. The platform operator is the highest level on the platform ecosystem. He selects and combines the services. If a service is missing, he develops it. Especially the developed services are high-level services, which are used to combine different subservices, some unique part of this platform. A general configurator, like basic configurator, can combine different subconfigurators for robots, grippers, sensors and stuff like that. He uses the specialized knowledge of the low-level configurators and combines it with a general overview. To get a better understanding, what differentiates microservices from other architectural patterns, we look on the separation of work. The separation on a classical full monolith is he develops visualization, logic and the data storage. So you have one team who have to accomplish every task. The next level is that you split the front-end team and the back-end team. You have some kind of separation of work. The last approach is like a front-end monolith and back-end microservices. In this approach, you develop back-end services which include logic and data and are combined via a front-end service. This is very inflexible because if the backend services changes one service, the front-end team has to adapt the front end. There is another possibility. As seen, the front-end monolith, you have a UI. The UI has special parts which is connected to the back-end services. And the approach we propose is a micro front-end approach of microservices. Every service has his own UI part, and this UI part is included inside a placeholder. If only the content of the microservice is changing can easily be included, there is no additional effort for adaptation. As an example, you have like the composition skeleton. This composition skeleton exists out of different placeholder. These placeholder are each placeholder for one service. The server-side rendering puts these service fragments together and deploys the rendered page to the customer or user of that page. To evaluate the approach, we created a 3-step multi-user configuration concept. Each configuration starts on the landing page. Where is it chosen? Whether a new session should be started via best practice selection or loaded from a previous saved meeting. In this example, best practices are successfully implemented or fully functioning solutions that can be used as a starting parameter for a new configuration. Alternatively, it is possible to join a session in progress. During a running configuration session, changed values and the chat are transmitted in real time to all simultaneously connected participants. If an administrator exports and downloads the latest configuration, it can be uploaded as a reload parameter to bring the latest state of the development to a further meeting. In order to utilize a multi-user configuration for enabling a division of labor, several roles are required. These can, for example, represent different functional units in the company such as project management, sales, purchasing, mechanics, electronics, or software. Each of these units has different competencies and objectives in a configuration process and therefore different authorization. In order to keep the prototype easy to understand within the concept, the multi-user approach was reduced to 3 roles and a total of 3 rights. In order to demonstrate that different roles can have different authorizations, the administrator has no restriction but is the only one who has the privilege to export the configuration. As an engineer, you may actively participate by being authorized to change configuration values. As a viewer, you can only participate passively and view the changes of the other participants and communicate through messages in the chat. In order to work independently with several teams on one software solution, a modularization into individual microservices is beneficial. The microservice teams can be grouped into 3 types: composition, without visual representation, and fragment microservices. The implemented microservice architecture should serve to allow different teams of large software projects to work together as independently as possible by clearly distributing the responsibilities. The main task of the composition microservice is to provide the HTML skeleton, including placeholders for embedded fragments and all links to the required CSS and JavaScript files. The composition services are landing composition to create a landing page, initial composition to start a session, and multi-user composition for the configuration. Their main task is to compile their service-specific style sheets as CSS and not to execute function code. In contrast, without visual representation services do not deliver HTML files either as a complete composition or as a single fragment. Accordingly, they are responsible for a certain task in the background. Two such microservices are used in the evaluation prototype: the API gateway and styling microservice. The API gateway is the only microservice that can be addressed by a client. It is the interface API to all the underlying microservice and is responsible for forwarding all incoming requests to the correct receiver. Requests can originate from a client as well as from another microservice. In this function, the gateway microservice or its Nginx web server is exclusively responsible for forwarding the incoming request unchanged based on the supplied path information. The fragment microservices provide one or more HTML fragments that are integrated in one or more views, respectively compositions. For example, the static components microservice is responsible for providing fragments that have little or no dynamic content, such as JavaScript, but have been integrated in a composition as a static components. In this evaluation prototype, the service delivers the header and the footer fragments, which are included in the view of all composition services. This allows changes such as adding another link in the header navigation bar or the web pages at a central point without redundancies. All microservices are individually deployed on a Docker container. Successful companies like Netflix, Spotify, or Zalando are using a microservice architecture too. Two services, the chat service and the configuration service, are WebSocket services and have a bidirectional communication. The configuration microservice, also belonging to the fragment microservice, is exclusively responsible for the status of all values in the active configuration. It is also responsible for delivering the configuration fragment, which is integrated in the multi-user composition and the communication with the server of the configuration microservice from the client side over the WebSocket connection. The multi-user composition microservice provides the basic HTML structure for the view of the multi-user configuration without adding a visible HTML part. Once the placeholders have been filled with a fragment of all services, the rendered HTML document is sent to the client. After the scripts have been executed, the WebSocket connection of the configuration fragment and the chat fragment to the server are established to fulfill the function of a real-time collaboration. The primary advantage of multi-user configuration is apparent. The page is composed of individual fragments all run as an independent microservice in the individual Docker containers. The authorizations of the configuration microservice, e.g. administration, engineering, or viewer, are set by the login role after the launch. The chat microservice is independent and only takes care of the bidirectional real-time chat. The visualization microservice fetches the values from the configuration microservice and displays them or updates them dynamically when changes are made. The demonstrator shown here is based on the project Robotop, aiming for a web-based configurator for robot-based automation solution. In general, the configuration process starts with a few filter questions to pre-select a best practice solution and start a new configuration. This is followed by a constraint-based modification configuration. To evaluate the concept, a prototype was implemented. At first, the Docker container have to be started, so the whole system is ramping up. After the system has been ramped up, the user login can begin. So the user can start a new configuration, select best practice scenario, and create a new user to join the new configuration session. Inside one configuration, the services work. To To demonstrate that the collaboration over the Node.js services are working, another user is joining the session. If one user uses a chat or says something, the changes are visible also for the other user. To demonstrate, we included different checkboxes, values, integers, drop-downs, every kind of data format is shown. After configuration, the solution could be exported and included by loading in a new session. This is accomplished with a JSON file, and another session with a loaded configuration is ongoing. Also, this session can now be joined. Down you see the running services and the underlying communication between the services to get a little impression about the communication between the microservices. In a nutshell, it was shown how a microservice architecture based on micro frontends can be used to enhance development and maintainability of engineering software solutions. Using the example of building a microservice-based multi-user configurator, it was shown that the development can be carried out by individual teams which can be grouped in composition without visual representation and microservice. The WebSocket fragments enable a multi-user session in real time, similar to the chat functionality which was realized with the chat. The configuration microservice distributes the current configuration parameter to all session participants. The visualization service only displays and renders its 2D and 3D scene according to the current configuration parameter. This type of microservice architecture makes it possible to flexibly enhance individual fragments in views, add new ones, or deliver views with user-specific fragments depending on the role a user is logged into. A special thanks goes to the Federal Ministry for Economic Affairs and Energy, which founded the project Robotop within the development of digital technologies PACE. Thank you for your attention. Now I'm at your disposal for further questions.
Welcome back, and thank you for your presentation, Eike. For those of you who just turned in during this presentation, this is the second live stream from the CIRPe Global Web Conference. As next, we plan to have a live discussion with the presenting author Eike Schäfer from the University in Erlangen. And we are going to continue our program in the same way. Hi, Eike, can you hear me? Eike, can you hear me now? I'm just turning to our technical support desk. We had a presentation, during the presentation a test call, and Eike was online. So Eike, just interrupt me please if you can hear me. And maybe I can start with the first question and we'll post it also on the YouTube channel if you can hear me, and then you can comment on it. So the question is about the challenges of possible industrial implementations of your approach, and what are the needs of companies for implementing your approach?
Thank you, Pinar, for this question, because if you see in production of cars, there are not only one company who can produce a car. So you have different companies who produces wheels, motors, and the stuff around it. And what you see at the moment at software development is that huge companies want to build every part of the software. And so you see some parts of the software are working very well, and others don't work so well. And also scaling is a problem, because if you develop huge functionality just for one part of a software, you don't have the business case. So if you have companies who produce specialized sub-services, these sub-services can be used in different software, and so you can put more effort in it to get a higher quality, and so the whole software landscape could evolve, because you have different customers. Compared to the car industry, some companies produce for different huge players parts, and so the quality gets better and better.
Thank you for your comment. Could you also specify some similarities or differences to typical interfaces which are available on the market?
The differences, it's like most of the interfaces on the market are very, I say, difficult to use because it's more like expert tools. And by using like this micro front-end approach, you can develop different front ends for different user groups. And so you can get much easier and more usable front ends.
Okay, thank you for your comments. I would like to thank you for the moment, and we will continue with the next paper, which is also presented by yourself, and then we'll connect to you after the video presentation again.
Thank you for the comment.
Bye.
Bye.
So I would like to thank Eike for the presentation, and we'll continue with the next paper from the Institute for Factory Automation and Production Systems from Friedrich Alexander University Erlangen-Nuremberg. The paper is entitled A Method for Collaborative Knowledge Acquisition and Modeling Enabling the Development of a Knowledge-Based Configurator of Robot-Based Automation Solutions. The authors are Eike Schäfer, Simon Fröhlich, Andreas Meyer and Jörg Franke. Please feel free to comment on the live chat on this YouTube stream on the right hand side, as you can see, and put your questions in there, and we will have Eike back on the phone after the next presentation. So we are looking to your next presentation, Eike.
Is Eike Schäfer of the Institute for Factory Automation and Production Systems of the Friedrich-Alexander-Universität Erlangen-Nuremberg, and I'm very proud to present our paper, A Method for Collaborative Knowledge Acquisition and Modeling Enabling the Development of a Knowledge-Based Configurator of Robot-Based Automation Solutions, in behalf of my colleagues. The paradigm of mass customization forces companies to offer products in numerous variants, providing proper solutions for individual customer requirements at the mass product price level. As the number of variants is increasing, configurators play an important role in tackling this challenge. One domain to meet individual customer requirements represents the planning of automation solution. In this domain, configurators promise a higher potential for efficiency increasing amongst manufacturers and system integrators. Of complexity of a system, such a robot cell highly depends on the number of elements and relationships, and often exceeds the complexity of the respective product, especially with regard to the complete automation solution. In addition, a robot-based automation solution combines the expertise of different engineering disciplines such as mechanics, electric, pneumatics, and software. In the conventional planning of such solutions, the collaboration of these experts is necessary. It is typically organized by a project manager with a significant amount of coordination work. The conventional planning process involves implicit knowledge, a dynamic, time-consuming response to long disregarding constraints, and independencies often resulting in so-called firefighting. To enable the development of a web-based robot configurator, and in order to benefit from the advantages of configurators, a method is needed to enable a simple and scalable development of the underlying logical configuration model, also allowing for a division of labor. So far, many knowledge-based projects are conceptualized by individuals or small groups. However, there is a lack of a procedure for the collaborative work on knowledge acquisition and modeling, especially for multidisciplinary configuration projects for mechatronic solutions such as a robot-based automation system. By transferring interdisciplinary knowledge about the planning of robot-based automation solution in an explicit configuration model, advantages of so-called knowledge-based systems can be realized. The term knowledge-based system is often used interchangeable with expert system, where the latter particularly refers to the capturing of a human expert's knowledge. In contrast to the human expert, the expertise is available with a constant performance, condensed, permanently, locally unbound, and immediately. This saves time and money and improves the quality and scalability when planning automation solution. However, in order to create such a configuration model, the expert knowledge must be found, extracted, pre-processed, standardized, and condensed. It is one if not the most difficult task in creating a knowledge-based configurator. In general, configuration is a special case of design activity where the artifact being configured is assembled from instances of a fixed set of well-defined component types, and components interact with each other in predefined ways. Among the other configuration tasks can be handled with three approaches: tabular, rule-based, and constraint-based. Tabular is a list of all valid combination of components, so no configuration system is needed, but the maintenance effort is very high. As an example, with just 7 robots, 4 adapter plates, and 4 gripper, 112 variations are possible, but only 11 of these configurations or variations are correct. Existing alternatives to configurators are classical lists in Excel, where all alternative configurations are manually stored, hard-coded programming solutions, which include implicitly the expert knowledge, existing enterprise software which is indirectly used for configuration, or the classical manual planning process without software support. Another approach is the rule-based approach, with production rules determining which components may be combined. It is easy to derive from natural language, but the maintenance effort is also higher than the constraint-based approach. Also, this approach gets very complicated to maintain with a higher number of rules. Out of these, the constraint-based configuration allows a model-based component-independent representation of the required configuration knowledge and is most scalable. Due to the model-based approach, the constraint-based configuration is used in the following concept. Existing methods for the development of configuration model alternate phases of individual work with joint workshops in order to synchronize the results, but are primarily developed by a central person. In addition, these methods are tailored for simple product configuration showing deficits in standardization and the creation of reusable, scalable knowledge elements. With special regards to interdisciplinary and collaborative work, further standardization is necessary. The method consists of 8 consecutive steps, which can be delegated to different employees due to their modular structure. The first 7 steps are executed sequentially in order to develop an appropriate configuration model. The last step also addresses a continuous refinement of the model by touching contents of all previous steps. While the method is generally applicable, it is explained using the example of a robot-based automation solution. The 8 steps serve as an agenda for the following presentation. In general, configuration offers a great potential but also requires a high initial effort and is only understood by a few people. That is why the first step, economically relevant use cases that are suitable for being mapped into a configuration have to be identified. The selection of a suitable use case is decisive for whether quick success can be achieved. For small and medium-sized enterprises, SMEs with fewer than 50 employees, only 1 in 5, and SMEs with fewer than 250 employees, only 1 in 3 use industrial robots for handling systems in production at all. Based on the market statistics, robot-based automation solutions for SMEs are identified with high demand and potential. In addition, half of the robotic systems in production are used for handling application. Following the Pareto principle, the focus of the aspired configurator for robot-based automation solution is set on the frequently occurring handling and then assembling scenarios, since robot-based welding is usually much more complex. The clear definition of an economical viable use case makes it easier for the management to release the necessary resources for the creation of the aspired configurator. Looking at the phases of the factory planning, the planning of robot-based automation solution addressed here can be classified in the area of rough planning and more precisely within the ideal planning phase. The ideal planning phase is characterized by 3 main steps. Firstly, the function and task determination of the whole production system and its individual resources. Secondly, the dimensioning of the resources. And thirdly, the structured positioning in the ideal layout. In the second step, best practice, i.e. successfully implemented robot-based automation solutions, are collected. These solutions serve as a knowledge base for the next step, as they contain implicit information about practical proven implementations verified by real operation conditions. In addition, best practice provide initial parameters for effort-reduced modification configuration. Documents such as specification, technical documentation, and existing digital models provide these data. Especially for facilities that do not have a large number of self-implemented automation solutions, this step represents a major challenge. Many system integrators regard the release of such information as very business critical. Only for sales support support purpose a transfer is conceivable, according to our expert discussion at the Automatica 2018, the lead exhibition for smart automation robotics in Munich. This challenge can be avoided via strategic cooperation with a system integrator, respectively domain expert. To ensure the transferability and scalability of the knowledge base, they should be based on a generic model and a norm description language. Therefore, the so-called SPPR model is introduced as a generic semantic model for describing production systems. As can be seen, the configuration model for robot-based automation cells includes scenario, product, and process as an input and the technical implementation itself resource as an output. This scenario containing general conditions and structural topological information for the automation cell. Serving as a starting base, it decreases the time required during configuration and limits the mathematical complexity for the solver. The product represents the objects and their different processing stages. The properties of the product set the requirements for the resources which execute the processes. The processes define the task for the resources and are used according to the standards such as VDE 2860 for handling and the DIN 8580 for the further operations. In addition to the user requirements, i.e. scenario, product, and process, the configuration solution represented by a set of resources is also included in the semantic model. The solution has a placeholder structure consisting of generic resource modules that can be instantiated as required by the given task. In the third step, abstract, generic topological elements are extracted from the best practices and information out of expert interviews and literature. All the elements needed for modeling the automation solution should be found in a so-called 150% topology. The SPPR model is represented in 150% topology. Topological elements are not only physical objects that are required in a robot-based automation cell to perform the manufacturing tasks, i.e. resources, but also general concepts involved in the planning process, such as manufacturing processes, product information, the surrounding area, management, objects, or human interaction. By gathering the different topology elements, the 150% topology is developed as a condensed general structure. Here the 150% topology can be seen and used for further configuration projects. The presented method focuses on the demand-oriented modeling approach where the data schema is based on the needs of logical queries. In particular, step 3 and 4 outline the primary challenge in the development of configurators, as these contain the condensed expert knowledge. In the presented cases, dependency knowledge between the elements is derived in the form of constraints. For this, a selection of use case relevant elements is extracted out of the 150% topology. In doing so, a two-dimensional assignment matrix is created holding all relevant topology elements on each axis. Each field of the matrix represents a binary relationship of the two affected elements. The matrix arrangement enables the sequential collection of the constraints in a well-defined workflow. Due to the standardized structure, several people or small groups can work together in a workshop in parallel. When assigning matrix elements, the knowledge engineer considers knowledge and strength of the persons available and involved, so the acquisition can be carried out based on the division of labor, like an expert for robots. In addition, white knowledge spots come explicitly visible through the matrix arrangement. This also enables the structured reuse of individual knowledge elements, respectively constrained from one configuration project to another. Missing expertise can be obtained through literature screening, expert interviews, or outsourcing. This way, the knowledge base can become extremely rich in content. Moreover, the detail level of the configuration can be easily adjusted by the number and the depths of constraints of a field. By the structure completion of a field of the matrix, all possible relations between the topological elements are considered. Based on the extracted constraints, it becomes obvious which logical attributes the given elements require in order to be executed automatically within a configuration framework. In order to be able to accomplish the knowledge acquisition process in a more structured and standardized way, a tool is evolved which primarily supports the steps 3 to 5 of the aforementioned method. The main purpose of the tool is to enable experts to formulate standardized constraints representing the primary configuration knowledge. In this way, the expert can semantically formalize his unstructured knowledge into a constraint via predefined elements and attributes. This enables the demand-oriented building of configuration models containing only required elements and attributes. Based on existing topological elements and their attributes, rules can be formulated and connected to queries. So there are two ways. One, you start with the existing topology and formulate rules and queries, or no topology is existing, then you formulate first rules and questions and use them to build up the topology. The tool supports the structured collection of scenario, objects, attributes, rules, and questions. The last three steps of the method addresses the integration and implementation automation in a configuration framework. In the sixth step, topology elements and their attributes data schema are transferred into the specific configuration language. Based on these, the constraints from the fourth step are added to the model referring to the element's attribute. The constraints are translated into machine-readable language given by the selected constraint-based configuration framework. For this process, the Tecton configurator and engine was used. In the seventh step, concrete components such as specific robots or grippers are instantiated based on the data schema. In doing so, the components must be transferred to a generic manufacturer-independent description. In the eighth step, the configuration model is tested and improved iteratively. For this purpose, the best practices are initially used to extract the underlying constraints. By entering product and process specification in the configurator, a solution, i.e. matching set of resources, is generated. Based on a possible discrepancy between configuration and best practices, further constraints can be derived. In this way, the configuration results gradually adapts to the real implementation. The presented approach consists of 8 consecutive steps, enabling the creation of an interdisciplinary, more standardized configuration model and a division of labor. First, use cases and best practices are collected. Out of these, elements are extracted. Using these elements, constraints and attributes are formulated and integrated into a configuration framework. Out of these, they can be refined and reused for future projects. By using a support tool, this approach is supported in a more standardized way. Thank you for your attention, and to the Federal Ministry for Economic Affairs and Energy for supporting Robotop along the technology program PACE. Do you have further questions?
Thank you, Eike, for your presentation. For those of you who has just turned in during this presentation, this is the second live stream of the CIRPe Global Web Conference 2019. As next, we plan to have a live discussion with our presenting author, Eike Schäfer, from the laboratory of Jörg Franke from University of Erlangen. Eike, are you online? Can you hear me?
Yes, I hear you.
Great. We have received 2 questions regarding your presentation. The first one is, what are the problems with general concept planning for robot-based automation solutions, especially for small and medium-sized companies? Could you comment on it, please?
Yeah, thank you for your question. It's a very interesting question. Like, if you go to the Automatica, you have 2 kinds of companies who are there. You have, at the one hand, the component suppliers like Schum, KUKA and Co. who sell the components, and then you have the system integrator who combine these components. And for the system integrator, you have huge companies who build like specialized engineering tools. But there is really no tool between for the calm SME to build automation solutions, because all tools are highly specialized and therefore only usable for like system integrators. And like, if you want a configuration solution for a small or medium-sized company, they don't have the highly expertized knowledge. So they know how to produce their product and they know their processes, but they have no idea about automation solution. And if they go to the exhibitions and then they see just, hey, buy a robot, buy a gripper and put them together, but it's not so simple. So to get it easier to them, you need like some guidance who, like, if you buy a car, takes them by the hand and then asks them only questions they can answer. So if you go to a car dealer, nobody would ask you like which screw size you want to use for your car. But if you buy an automation solution, sometimes people ask you so specific knowledge you can't answer because you're not the expert for this. And so this was the aim for the configurator, just to ask questions you can answer and map these questions in the logic behind to the technical solution. So you don't have to choose what you need because you don't know it. So you just answer what the process and the product is you want to produce.
Yeah, we're listening to you. Sorry.
Yes. That's all to this point.
Okay. Do you see, I mean, Of course, it's an industrial challenge especially for small enterprises also to invest in such new tools. Do you have any approach which can be used easily or implemented easily in an industrial environment, or are you working on it?
Yes, thank you for your answer. Just mention the picture shown in the live stream is not me. And
sorry for the mistake, we just corrected it. You are going to see it in a second.
Yes, and to the question, yes, we are doing it. I can just post the link also in the live stream. We're a government-funded research project, and at the moment we have some live demonstrators which can be seen at the Automatica 2020. There we will be in the exhibition stand for the Bundeswirtschaftsministerium, and there you can test the tools when we want to address also a huge audience. And there we make a lot of user tests. So we developed on the one hand user-centered prototypes to test it with end users, and on the other hand we discussed with a lot of system integrators and experts to combine this knowledge and like to make a lot of field tests for usability, for configuration, integration, and we have a running system, but at the moment it's just a closed beta testing, so it's only for the project involved participants. But if you want to have more information, I just posted in the live chat, we have a homepage where you can find further information to the research project.
That would be great. It would be great if you could post your web link for the project, as well as if you have any information about your exhibition next year, that our audience can follow the next steps on this approach. The next question regarding your paper was about the future work. Actually, you mentioned that you would like to simplify the 8 steps you just presented. Could you detail how would you like to combine them, or would you like to simplify them for which purpose?
Okay, for the first step, like simplification is necessary because we want more explicit work sharing. So at the moment, you have some experts who have, I say, the God brain, who has to know it all. But like to get better scalability, you have to have better work separation. So one aspect to make it easier is to develop specific tools like Excel tools for start, and then make them like with Java or other higher concepts. So you are guided through the process. Also, you can use like BPMN 2.0, also business process modeling and notation to model the workflow and make it automatically runnable. And also we are building at the moment templates. So if you are doing some specific task for this process, you just can fill out the templates and don't have to think about the structure. Mm-hmm. And the last step is like we built like some semantical models in the background. So to get further standardization into naming and other stuff. So for this we have also a paper which is ongoing at the moment.
That's great. So we are going to follow your next publications and we'll learn more about the simplification. Thank you, Eike, for your time, and hope to see you soon.
Thank you.
Bye. So we are back on Livestream 2 and have already listened and watched 4 presentations and had some questions and answers with our corresponding authors, presenting authors. So we are going to continue for the next hour with further presentations. The next one is from the Machine Tool Laboratory from the WZL Aachen. And the contributors are Christian Brecher, Stefan Wein, Xamoy Xu, Simon Storms, and Werner Herfs. The paper is entitled Simulation Framework for Virtual Robot Programming in Reconfigurable Production Systems. We are looking forward to your video presentation.
Hello, my name is Stefan Weyen and I'm working at the Laboratory for Machine Tools and Production Engineering at the RWTH Aachen University. In this presentation, I'm going to present to you my research work on the simulation as a service framework for virtual robot programming in reconfigurable production systems. First, let's think about why do we need virtual robot programming? In the industry, especially for small and medium-sized companies, the robot programming by teach-in is still state-of-the-art. And because it requires expert knowledge, it is not suitable for non-expert users. Thereby, the translation to other domains, like biolaboratory work, is slowed. Other approaches allow easy-to-use robot programming by guiding the robot manually. This is especially used when programming robots for human-robot collaboration. However, when having a flexible reconfigurable production system with a higher number of changes, this type of programming exceeds the range of efficient usability. Virtual robot programming can close the gap by anticipating certain activities. Depending on the maturity level of virtual commissioning, the effective cost of commissioning can be reduced significantly. Now let's take a look at an exemplary reconfigurable production system. In one of our research fields, we are focusing on lab automation. A central demonstrator is the iCell Factory, a reconfigurable automated production platform for stem cells. The system consists of a base system and 3 positionable modules for laboratory devices. In the following, the system is used as an exemplary use case to demonstrate the functionality of the framework. What happens when the plant's physical configuration is changed? We need to update the virtual environment. Modules or components can either be removed, added, or modified. But how is it done? Different sensors can be used to measure objects' positions in a three-dimensional space, for example via vision systems. The measured position, orientation and the object's ID are then written into an asset administration shell, which are instantiated for every module registered in the data management. The asset administration shell also contains a watchdog system, allowing the recognition of parameter changes. In case of changes in position or orientation, the shells actively request a simulation service, providing all relevant data to it. After the robot path planning is done in the simulation, the paths are written into the respective asset administration shell again. There, the control system can access the information and execute certain robot operations. The paper related to this presentation focuses on the simulation as a service approach. Our proposed simulation framework is based on a service-oriented architecture. To structure and modularize the simulation, it is split in main services and sub-services. While main services always host sub-services, the specific set of these sub-services can be changed on runtime. Thereby, the simulation can be adapted to the needed requirements. For example, a sub-service to ensure safe transport of open liquid vessels can be included. To support this adaptable framework, a method is required to combine different sub-services. By defining a so-called pre-service description for the required data of a sub-service and a post-service description, returning the resulting output of a service, multiple services can be linked. The service description can be semantical and/or numerical. For example, a sub-service for composing the virtual cell requires a kinematized CAD model. This requirement is defined in the service's pre-service description. Another subservice, preparation of models, returns these models as a result. This information is captured in its post-service description. The final information set is also given as the post-service description of the respective main service. Now let's take a look at some selected subservices of the framework. In order to set up the virtual environment, prepared module models are required. Therefore, the CAD models of the modules are extended with oriented vectors, defining collision spaces, interaction points, search points, and initially the position of modules matrix code. The collision space vectors are later used to reduce the model's complexity while simulating, reducing processing time. Interaction points define deposit positions of modules for objects manipulated by the robot. To reduce the amount of possible robot paths and enhance the algorithm speed, search points can be defined. For modules with an internal kinematic, internal axis can be defined, allowing an extended collision check. Models prepared with the subservice are saved within their corresponding asset administration shell and can be requested from other subservices. For example, when setting up the virtual environment. For path planning, we propose a subservice divided into 4 process steps that are processed iteratively. First, the start, search, and end points are checked for validity. All points must be reachable without any collision in a static pose. In later iterations, all the intermediate points are checked. In the second process step, a path planning algorithm based on rapidly exploring random tree searches for nearest neighbors using KD trees. Then the intermediate points are interpolated, and the movement is checked for collisions. In case of a collision in the movement or condition validity check, the interpolation's intermediate points can be reused for setting up the path. The transport of open liquid-filled vessels via a handling robot is an important application in lab automation. To demonstrate the adaptability of the framework, 2 different but combinable subservices to avoid spilling liquid are used. The first one utilizes the adaptation of the TCP's rotation. Spillage depends on multiple parameters, for example, the acceleration. As the literature describes, liquid can be modeled as a pendulum. The acceleration is proportional to the displacement angle, and spilling liquid can be avoided by correcting the TCP's rotation angle depending on the acceleration profile of the TCP on track. The second subservice concentrates on the rotation angle of the TCP and its dependencies from the robot configuration. Thereby, the rotation of the TCP is not fully inhibited, but restricted to a limit of 10 degrees in maximum. As you can see, different robot configurations result in varying robot paths with different rotation angles of the TCP during movement on the paths. The orange lines show the movement from one intermediate point to another. When the line is red, an additional collision has occurred. The goal is to find the optimal configuration for each path and ensure a safe translation between different robot paths. Once the optimal robot configuration is found, the full path has to be checked for collisions in the movement again. A combination of the 2 subservices can achieve even better results in avoiding spillage, but also reduces the number of possible paths, as additional collisions have to be checked. The evaluation of the subservice indicates its usability for the application, as the rotations around the TCP's X and Y axis show only slight deflections for multiple different paths planned with the algorithm. In this exemplary path, the deflection is underneath ± 10 degrees. Stable robot path can be achieved using the subsurface. Let us make a short conclusion. The usability of the simulation framework was demonstrated for an exemplary reconfigurable production system. Also, the framework shows high potential for adaptable simulations in simulation as a service applications. The subservice for liquid handling based on robot configuration shows good results. In the future, the framework's evaluation has to be extended to other production systems. Additionally, a fully automated setup of virtual environments and an improvement of the subservice for liquid handling is considered. Thank you very much for your attention.
Thank you very much to Stefan Wein from the Machine Tool Laboratory of WZL Aachen, Germany, for sending us this video. For those of you who has just turned in on the live stream, we stream on from today to Friday the CIRPe Global Web Conference on 2 live streams. One of them is on this channel and the other one is on another channel. You can find the link just below to this video. And if you would like to post the conference on any social media, please use the hashtag CIRPe. This online conference is scheduled as follows: that we have a video after each video presentation, a live discussion with the presenting author. And for the last paper, which is entitled Simulation Framework for Virtual Robot Programming in Reconfigurable Production Systems, we have our presenting author, Stefan Wein, on the telephone now. Stefan, can you hear me now?
Yeah, hello, Stefan Wein here. Thank you. Nice to be here.
Nice to see you again. So, so there is one question regarding your paper about the boundaries of the of your approach of the framework for real-world applications. Could you detail on that, please?
Yeah, thank you very much for the question. So first of all, this concept is demonstrated currently in the production system we also mentioned in our paper, the ISO factory. So it's a system for cultivating iPS cells, so stem cells. And we currently implement this framework to this production system and try to really make it work. First of all, we have this. We have 2 parts, so 2 main parts. This is the one from the sensors, which need to be integrated. This is working. Also, the simulation is working. And now, where's the border between having a real system and a simulated system? So only with CAD models. This is where we have some divergences. So it's not the same. We have some issues regarding the correctness of CAD models, of course. But if we say, okay, we have CAD models which have which are correct or which are optimally made up and have a good set of the geometries, we can really have make this system run, and we have not that much divergences between those. But there are 2 things. First of all, we need to match the CAD model and the real boundaries again by having a reference measurement. So we measure the reference distance or vector between a code, so this is a data matrix code, which is on every module and on a position where the interaction between robot and the module takes place. And by doing this, we can really set a really good configuration of the virtual environment, and this works out really well till now.
Okay, sounds great. And for positioning and also for further measurements, do you use any sensoric data, or what do you use for your approach?
So we thank you again for the question. So we first of all we use the camera data, but also we have integrated another sensor which is based on kind of laser measurement, doing a position, just a relative positioning measurement. So we have the absolute positioning measurement done by the camera. So we have two cameras which are just scanning the working space, and on the other side we have the two sensors for every module, which does scan the relative position. And so what we can show by this is that we can just add new sensors to it, and we can do a data fusion. So we just use the basic absolute data coming from our cameras, and we just add the relative position coming from the sensors. Also, we have tried to use some other sensors like acceleration sensors to measure slight position changes of objects. And this data can also be included there. And all this data comes to this data management system where we have these active asset administration cells, which just put the data together to a new data set, which is done by rules which are implemented. And afterwards, the service, like the simulation service, can just be automatically enabled. Sorry. Yeah.
Okay, thank you for your answer. There's another upcoming question. If you have any benchmark to other approaches in a similar with a similar data or data set.
So we currently the first benchmark we had was this production cell, but we are planning to do so in the next step, because we want to find out where are the boundaries of this full concept, and also where we need to adapt our framework in order to make it able to run for every kind of production cell. Currently, we are able to just put in new modules, of course, but also other robots into this cell. And it's just defined by the CID model we have from the different objects and also the cell itself. We can just put in any kind of other cell too, but we need to really verify it now. Yeah.
I see. Thank you for your answers, Steffen. Have a nice afternoon and talk to you soon. Bye.
Thank you, and same to you too. Bye.
Bye. So we are back on Livestream 2 for the CIRPe Global Web Conference 2019. Our session is entitled Automation, Planning and Configuration, and we have two remaining papers today. So the next paper is from our colleagues from the Karlsruhe Institute of Technology from Germany, and the authors are Carmen Krahe, Maximilian Eberl, Alexander Jacob, and Gisela Lanza. The paper is entitled AI-based computer-aided engineering for automated product design, a first approach with a multi-view based classification. We are looking forward to your video presentation.
So then, hello everybody and welcome to the presentation of my paper, AI-based computer-aided engineering for automated product design, a first approach with a multi-view based classification. So my name is Carmen Krahe, I'm the first author of this paper, and I'm from the Karlsruhe Institute of Technology, especially from the Institute of Production Science, WBK. So what is the current initial situation we are confronted with in our paper? We say that in a lot of companies there exists a large amount of already existing CID models, and those CID models contain a lot of experience and knowledge of designers, because those CID models, respectively the corresponding products, have already been successfully produced and sold. The problem is that this implicit knowledge is so far not formalizable, so it's not possible to possible to express this knowledge in rules, and so it can be handed over to other designers, to new designers, and to unexperienced designers. So what we try to do now is to use methods of machine learning to make this implicit knowledge formalizable. And therefore, we develop some kind of design assistance, which on one hand shall support especially inexperienced designers or engineers in a design process, and on the other hand, which shall relieve designers from repetitive adaptations, for example, caused by divergent requirements, standards, and dimensions. And the idea is then to save time and also costs, and mainly to give the designers more free space for real creative work, which we can't replace by methods of machine learning. So how does our solution looks like? We try to extract common design patterns for different component classes from the existing CAD models. And on basis of this, it's the idea to propose next design steps. Or some other thing is to also indicate already existing very similar CAD models to the designer in order to avoid the design of duplicates. So our database, just like I said, is mainly contained out of CAD models, which contain implicit experience knowledge of designers. On the one hand, in form of pure geometric information, for example, information about the shape of the CAD model or the different dimensions, just like height, width, and length. And on the other hand, this is the so-called design history or model tree, which is the sequence of design features a designer used to build up this CAD model. And the model tree also contains the corresponding parameterization of those features. And you can imagine a feature, for example, just like extrusion of a cuboid or a drilling or, for example, a rounding. And what are we gonna do with this information? The geometric information we mainly use for a classification task or similarity analysis in our approach, and the design history we want to use to propose real next design steps to the designer in form of next features. So how does our approach looks like? We have a three-stage approach, and the basis for our approach is first to make some component classification in order to categorize the existing database, and so to enable a designer to find a suitable CAD model more quickly. And therefore, we first make some classification, and then we try to propose in between one component class the most similar CAD model that already exists. So this is the basis. And the next step is then to classify semi-finished components during a design process. This means that our design assistants shall recognize during a designer or designers designing the product which component class is currently under design. And then if it has recognized which component class it is, it shall look in the existing database of this component class if there maybe already exists some very similar CAD model, which is then proposed to the designer in order to avoid the designing of duplicates and to save time. And the next step is then not to propose a complete CAD model, but to propose real meaningful next design steps to the designer. And therefore, we also have to recognize first which component class the designer is currently designing, and then the design assistant tries to propose in this component class real meaningful next design steps, which it has learned from the existing data and the contained design patterns of this data. So here, for example, the designer designs some lid, and the design assistant proposes a next design step in form of a hood. So what we did until now is the basis. So we first considered the pure component classification. So in the existing literature, there are mainly four different state-of-the-art approaches how to represent 3D models to process them with methods of machine learning. So one approach is the so-called multi-view approach from Su et al. And introduced in 2015. Another approach is to use graphs to represent 3D models, for example, done by Simonovsky and Komodakis. It's also possible to use point clouds to represent 3D models, for example, done by Sedergaard et al. In 2017. And the last approach is some voxelization of a 3D model, and you can imagine voxels like a 2D pixel. And for example, Key et al. Use this approach. And all those authors I mentioned mainly used this 3D representation form to make some classification task. So what we did now in our approach, we used some adapted variant of the multi-view approach of Su et al. So what is the goal? Of course, we try to classify components, and the aim is to order the available data to find components more quickly in the existing database. And the classification is also the basis for the classification we want to do with semi-finished components during the design phase. So our approach first defines some kind of standard orientation of the components, which is determined by 5 different conditions. Then we create 2D images of the 3D objects from different perspectives, and the 3D objects therefore were aligned in the standard orientation. And lastly, we classify those 2D images via convolutional neural networks. So therefore, we trained perspective-specific CNNs to classify those 2D images. And as you can see on the picture on the bottom right, we used 26 different cameras, so 26 different perspectives, and combined the opposing perspectives into one CNN. So this means that we had 13 different CNNs for our 26 different perspectives. And in the end, we pooled the perspective-specific class probabilities into an overall forecast. So we made some proof of concept of our approach with the ModelNet 10 database, which was introduced by Wu et al. In 2015. It contains about 4,900 3D models of 10 different categories of furniture, and you can see here in the picture some examples of each category. So first of all, just like I said, we determined some kind of standard orientation with respect to a defined base perspective, as you can see here in the picture. The next step is then to generate 2D images from the different perspectives. In sum, these were 26 different perspectives. Again, you can see it here in the picture, and on the bottom right, you can see the 2D images of a spatial level here on the example of a sofa. And in red, you can see the 2D image of the base perspective. The next step is then to train the perspective-specific CNNs with those 2D images we get in the way I just explained. And the classification is then done by a pooling over all perspective-specific class probabilities. So we summed up all probabilities from the perspective-specific CNNs. So in sum, these were 13 different probabilities for the 26 different images. And then we calculated the average over these probabilities, and this is our final class assignment. So how does our results look like? You can see here on the left the accuracy, and on the bottom the perspective-specific CNNs. And as you can see, the accuracy of the single perspectives varies between about 68 and 84%, which is quite much. And we also have large difference depending on our model category. For example, toilets are classified quite well in all perspectives or in all CNNs. But in contrast, for example, tables have a very large scale of the accuracy, or also dressers and or desks. So our overall accuracy we achieved overall classes is about 88.4%. And you can also see it by the red X. It's the overall classification accuracy. So here on the picture, you can see the confusion matrix of our classification task. And as you can see, often the assignment is not clear, especially here in the class desk. Only 58% desks were classified correctly, and for example, 18% were wrongly classified as sofa. So what is the reason for this? We found out that objects often look quite similar from certain perspectives. For example, a sofa and a desk both have a square base, and so both look quite similar from one perspective. For example, you can see it here on these pictures. In the third column, we have the class desk from two different perspectives, and for both perspectives, the 2D images were wrongly classified as sofa. So on the bottom right, you can see the picture of a sofa from these perspectives, and probably the CNN learns to link this angle shape more to a sofa than to a desk, and that's the reason why those desks were here wrongly classified. So what is the conclusion for us from this? We found out that the multi-view approach works quite well if the classes are quite different, but for example, on the example of the class desk and sofa, it's it's necessary to look more into detail, so to try to represent more those inner structures, and therefore in next investigations we, for example, try this classification task with the help of graph-based approaches, which are able to represent those inner structures in more detail. So then, thanks for your attention, and I'm looking forward to your questions later.
Thank you, Carmen, for your presentation. For those of you who has just turned in, we are on live stream 2 of the CIRPe Global Web Conference Day 1. As next, we plan to have a live discussion with Carmen and discuss your questions you have posted during the video. Other than this, we have another live stream. Also, if you put the link below, live stream 1, where we have started today with the opening session of the conference. So I'm turning left to my colleagues and I would ask you if, do we have a connection to Carmen? Carmen, can you hear me now?
Are you able to hear me?
Yes, great.
Yes, okay, cool.
Thank you for your presentation and being with us now. The first question I have is, what are the challenges of industrial applications for your approach?
So there we have several challenges. I would say one main challenge is to integrate our approach into existing CAD software, because in our project we are working with PTC Creo. It's a common CAD software, and so there we have to investigate special APIs. This is one problem, but I think one major problem is that we first have to gain the confidence of the design engineers, because I talked a lot to engineers and they told me, oh, I'm afraid of being replaced by machine learning. And another thing is that I also want traceability and understandability. So if we, for example, propose next design steps, there's the problem that a designer wants to know why the assistant system says this, and that's a thing we have to work on in future work.
Okay.
And I think some other point is also that in a lot of companies the CAD models are labeled quite bad. So for the classification task, which I was presenting in my presentation, we need labeled data, and this is some other problem because especially the companies we are working with, their databases are more or less unordered. So this is some other challenge we have to meet.
Okay, thank you. Do you compare the perspectives one-to-one or also between different perspectives in order also to connect, for example, with mirrored models?
You mean that we just change some perspectives? I didn't get a question right.
Yes, I mean, do you compare the perspectives to each other one-to-one, or do you have a connection between them, between mirrored or simulated models and also the real perspectives?
So we had 26 different perspectives, and just like I said, we always combine two perspectives, the opposing perspectives. So we had 13 perspectives altogether, and for the classification, we combine all perspectives. So
Okay.
yeah.
Please just go ahead.
I didn't just get a question.
Maybe I can ask our commenters to specify the question. And in the meantime, I would like to ask you about the future work you are going to do. Do you have new approaches based on your results, which are presented in your paper now?
Yeah, we also worked on a graph-based approach for a classification task, because one problem, like I said, is that only visual view of an object is not enough, because we have to represent the inner structures, and for this we worked on graph-based approaches for the classification. And we also tried some first approaches on proposing the next design steps. Therefore, we used recurrent neural networks, and we trained them based on the sequences we extracted out of the CID models, especially from the part files. So this is the so-called structure tree.
Thanks for your comment. I just see that our commenters type on the chat.
Okay.
So, there's the specification of the second question. Let me just read it to you loudly. Do you compare every perspective with the 26 perspectives of the other product, or just one by one?
No, we just compare one by one.
Okay. Okay, thank you a lot for your answers, and thank you for connecting to us today.
So thank you a lot too.
Hope to see you soon. Bye.
Yeah, bye.
So we are back on Livestream 2 of the CIRPe Global Web Conference, Day 1. Within this session, Automation, Planning and Control, we come to our last video presentation from our colleagues Alexios Papakaralampopoulos, Panagatios Stavropoulos, from the Laboratory for Manufacturing Systems and Automation of the University of Patras from Greece. The paper is entitled Towards a Digital Twin for Thermal Processes, Control-centric Approach. We are looking forward to see your video presentation.
Hello, my name is Alexios Papakaralampopoulos, and I am going to present to you our work entitled Towards a Digital Twin for Thermal Processes, a Control-centric Approach. It is a joint work between myself and Professor Panos Stavropoulos. We both are with the Laboratory for Manufacturing Systems and Automation in University of Patras in Greece. Here you can see the contents of the presentation. First, the context of the current work is given, and second, introduction follows, namely how dynamic systems can be adopted as digital twins. Then the strategy is given, and what follows is the complexity in modeling. Number 5 is adopting and studying switched systems, while number 6 is the possibility for process control. Then the dynamics change within the evolution of the process are given, and finally, under automating decision making, how Amdahl's law is used. What is given then is some conclusions and future work. Some words about our context. It derives from an EU project called Integrate. It is a project on additive manufacturing. Its major goal is to develop a novel end-to-end solution capable of demonstrating the potential of directed energy deposition processes. Some keywords that can be used to understand the concept of integrate are optimization, control, and inline quality assessment. This, of course, needs to be done through modeling and under the prism of mass customization. So, as being apparent, the concept of digital twin will be extremely useful in our case. As aforementioned, there is need for enhancement of manufacturing processes in terms of optimization and control. What is, however, required in any case is having a corresponding model that will allow describing the behavior of the system and at the same time be able to test and or design the controller in real time. Data-driven model seems to be able to be utilized as a digital twin as long as formulating the system as a dynamic system is feasible. In the meantime, the distant goal is to control the process efficiently with respect to main manufacturing criteria. So there has to be some sort of matching between control theory concepts and manufacturing process performance indicators such as temperature tracking error and quality, temperature tracking raise time, and H2 norm of the input signal as energy. A framework for optimizing or controlling a manufacturing process is going to be introduced through its characteristics. The framework under which the current work is developed has to do with retrieving a digital twin through utilizing a dynamic system as a real-time model. This model has to be adaptive towards the real laser manufacturing process through monitoring, and at the same time it has to be used in order to design a controller no matter how complex the process is. The characteristics of the strategy are that first, the human is kept in the loop while there are automation attempts. Additionally, it would be good for the model to be self-evaluating. The strategy itself is that we are going to use a dynamic system that will represent the process itself, a laser-based process in our case, and at the same time it will be used to control the process. The digital twin will thus be able to operate automatically the process, provide intuition to the user/operator, and be able to give responses to what-if scenarios. These are all apparent in the loop of the diagram. Schematically, the digital twin and the dynamic system are given separately for the sake of generality. The models by themselves, however, are not going to be simple. Nodal temperatures are affecting each other through various phenomena such as conduction. Even in the case of a linear discretized system, their mathematical relation will be complex, involving the existence of many transient functions. Our goal is to manipulate this complexity. It seems that we can handle this situation through specific models requiring more than one dynamic systems. Two or more sets of dynamics are considered as coexisting and interchangeable. The changed dynamics can be deterministic or stochastic and can be up to the input or the output, or even a state variable. There may be also need for smooth change, which make models slightly more difficult to handle. In our case, it can be the evolution of temperature itself that is used as triggering. To illustrate this phenomenon, two different responses are given below. On the left, we have considered linear change in a profile involving heating up and cooling down, while on the right, also phase change is considered. In both cases, the simulation with switch systems, annotated in red color, seems to enhance the performance of the simulator with respect to single dynamic system. In green, the vertical lines are indicative of the change in dynamics triggered only by temperature and its derivative. It's apparent that the rhythm, also known as time constant of cooling time, cannot be handled by the same system as heating up. There are this way also possibilities for process control through applying control theory. It is mentioned here that when controlling a system, there are two candidate positions of the controller, one for tracking, on the feed-forward branch, one for stabilization, on the feedback. In the diagram on the right, you can see that a single controller can be used to enhance the system regarding tracking. Input may have to be regarded as temperature here. Retrieving power signal may get tricky though. However, not all things are simple here. We will proceed the illustration with designing a bank-bank controller, meaning an optimal controller averaging tracking with energy efficiency. There are constraints in the laser power itself. For example, input signal can take only 2 values. For this case, the modeling has slightly changed. You can see the fluctuations in the system output, which means that the controller indeed changes states, while there has been added a delay in the observation/control signals for the system to be solvable. All this concludes to the fact that the closed-loop system performance has to be checked, since we have gone a bit away from the theory. What is more, the controllability of the process is not the same everywhere. One can form tables as the ones shown here. Various cases have been considered, with the system considered as a whole or separately heating up and cooling down, with phase change as an extra option, linearizing the behavior, of course. Then, 3 different numerical aspects related to controllability matrix are shown, namely the determinant, the rank, and its condition number with respect to norm 2. According to this table, the controllers are expected to have different impact on each phase, making the system even harder to control. This is even evident through studying the behavior with root loci. It can be easily spotted that depending on the phase of the system we're interested in, namely heating up, cooling down, etc., first, the behavior changes in terms of time constants, overshoots, etc., and secondly, the controller appears to affect differently each phase. This may affect even the stability of the closed-loop system, which is unwanted. As a result, a controller has to be switched or robust enough to handle every one of the situations come across, regardless of course of the uncertainties deriving from the material or the process. Since we are in the direction of creating a digital twin that can be used to optimize the manufacturing process, some meta functions would be extremely useful. So, towards automated decision making, from computer science we can adopt Amdahl's law. So, in a system of subsystems, if we accelerate to another subsystems of size p by s, then the whole system is going to be accelerated by s latency. In our case, we can divide the process down to heating, melting down, and cooling down. To show how this can work, we suppose that we accelerate heating up by percentage s. 2 different cases are regarded below. Laser welding on the left, where the total acceleration is around 25% for P equal 50%, and additive manufacturing on the right, where cooling down is more important and where a total acceleration can be found around 10% for P equals 20%. Depending on the process and the case in general, we can decide if this change in the controller, which is complex by default, is profitable or not. So, we have come to a point where some conclusions can be given. Under the prism of creating a process-level digital twin, laser-based manufacturing process modeling is reconsidered, and the combination of dynamic models through switched change in dynamics has been used. The controller itself, even if it is considered to be a static gain, can be quite hard to be obtained through an analytical procedure, as the dynamics are quite challenging. Understanding the dynamics of each phase, meaning heating up, melting and cooling down, seems to be of high importance towards being able to control the process itself. This is highly evident by the change of position of the identified zeros and poles on the complex plane. Finally, depending on the process itself, the margins for improvement are case dependent, and complexity of the control design may even delay the introduction to the market. Regarding future work, in order to integrate such methodologies to a greater extent to digital twins, further matching is required between physics, such as melting, front propagation, convection and conduction, and behavior of the dynamic system in terms of relaxation times, overshoots, etc. As such, this will further enhance both monitoring in terms of placement of the sensors and control, for example, adding extra criteria or other conditions. Evaluating the need for a controller through the digital twin or empirically verifying metrics related to control applicability is highly suggested. Examining such controllers in near industrial environment, as well as to study the behavior of such closed-loop system utilizing dynamic controllers, is suggested. Considering efficiency in terms of controller design time and system ramp-up should be considered as an additional metric, and studying the repeatability of such controllers for different kinds of lasers and different kinds of materials is also suggested. That's all from my side. For identifying data and methods used, you can go and see a reference of this publication. Thank you for watching this presentation.
Thank you very much for sending us your video presentation. As next, we plan to have a live discussion with the presenting author of the paper Towards a Digital Twin for Thermal Processes. The presenting author was Alexios Papakaralampopoulos from Laboratory for Manufacturing Systems and Automation from the University of Patras in Greece. Alexios, can you hear me now?
Again, loud and clear.
Great. Good. I would like to ask you two questions. One of them is, do you plan any industrial implementation of your approach?
Yes, indeed. This was a proof of concept, and it proved numerically that control can occur through a digital twin implemented in this concept, and the concept presented. But regarding industrial, actually even more experimental work, further elaboration has to be needed. We are preparing such works, but there are of course limitations to what we can do with technology now. What has to be done first is verification in lab conditions, and then we can move on to an industrial-like experiment that can prove undoubtedly that this can be done, and this is feasible in industrial environment.
Mm-hmm. Thank you very much for your answer. Are there any further boundaries for the control-centric approach?
Yes, it's quite a few of them. First of all, there's the measurement. Sensors themselves have to be utilized in such a way that they are integrated into the digital twin, because you can only measure temperature on the exterior of the part, and you need to make some estimations for the inside, which has to be done through models. The sensors themselves, there are some approaches. For example, there are multispectral cameras that can be used to this end, but they need to be customized through the models, because each part, each material used in even under experimental and under lab conditions has to be tailored. They need some sort of calibration in order to work for our case. Also, the control of the machines is not straightforward. First of all, you need to control the variance in the power, and then you need to insert some sort of controller that can change in real time the power of the laser. For example, if we're talking about purely thermal processes. So there are obstacles in both monitoring and control side of this control-centric approach.
And your future work is going to concentrate on those challenges to keep them.
Among other things, yes. Hopefully we.
Thanks a lot for your time, Alexios.
Thank you too, and congratulations for the organization.
Thank you. Have a good afternoon. Bye.
Oh, bye-bye.
So we come to the end of the session, Automation Control and Planning and Configuration, on the live stream 2 of the CIRPe Global Web Conference 2019. I would like to give you a briefly overview about the conference program tomorrow on Friday. Tomorrow we are going to have 2 live streams as today, and our subjects are going to be on the live stream 1, where you can find the link just below of this video, 3 different topics. These are form-based processes and metrology, cutting and grinding and spindles, as well as value streams and lifecycle engineering. On our stream, which means on this link on YouTube on the live stream 2, we are going to have 2 sessions. Paper sessions are based on robotics, automation and assembly, as well as additive coating, hybrid and incremental manufacturing. Tomorrow's sessions are gonna start at 11:50 German time, so please adapt to your time, and we are gonna end around the same time, which means around 4 p.m. German time again. On Friday, after a short opening session on 2 live streams and a paper session with 3 presentations each about value streams and lifecycle engineering, we are going to have the next special issue of our conference, which is the industry panel discussion. For the industrial panel has already had a look at your papers and gave you some scores and feedback about the paper. So you are gonna get the chance to talk to the panel and discuss with them in detail their feedback right directly to your paper. And we plan to end the Friday sessions around 1 p.m. German time. Please feel free to post your contribution as well as the conference in any social media channel. And if you do it, please hashtag the conference with the hashtag CIRPe. Please also feel free to comment on live chat as well as through other channels to us as organization committee. And I hope we were able to owe the privilege of your time today, and look forward to meet you on stream 2 tomorrow again. Have a good afternoon, good evening, and good night. Bye.